Hello everyone, welcome to this new technical webinar that we are producing today. I am David Romo, Product Manager at iTechSoft company, and I'm proud today to introduce you our new software C-NEWTUN, also called Software Wizard for 3D finite element analysis of tunnels. Today I will introduce you our company and why we developed this C-NEWTUN software. I will present you several features so that you will know what you can do with C-NEWTUN, and more important, I will sum up all the benefits that you can get by using. As you see here on this screenshot, C-NEWTUN is a part of our more general CESAR 3D software. CESAR 3D being a finite element software for all geotechnical and other civil engineering projects. Inside this software, C-NEWTUN is an option proposing several grids with explicit and intuitive text and context. From this, we will generate all the geometry and the 3D mesh. This in an automatic way, and also we will edit all the stages of construction. Finally, after optimized calculations, user will access a specific result so that he can complete his report for his tunnel project. So coming back to who we are, iTechSoft is an IT company with a strong background in software edition, distribution and support for all professionals in civil engineering. Next year, we will celebrate our 14th anniversary. And every day we are providing support and training to around 2,100 customers through in our support for all our software catalog, including Accor for structural analysis, and other products that we are distributing, like the program Geo5 for geotechnical analysis, and also Alizé for pavement design. iTechSoft has a long-time relation with a renowned institute in France, like Université Gustave Eiffel and CETU, Center for Tunnel Studies. We also have a strong collaboration with engineering companies through research and development programs, and C-NEWTUN is the result of one of these programs. As said, C-NEWTUN is an option of CESAR. CESAR is a finite element software with a strong history on tunnel analysis, and especially in 3D modeling. If we come back to year 86, we can find some results of analysis of the channel tunnel, for example, a tunnel that links UK and France. Nowadays, in our commercial version, user in 2D can model several types of model and all the soil structure interaction that are required for accurate modeling. Also, with our strong background in 3D models, user can either define I would say standard or complex geometries and generate all the relevant models, as illustrated here, several galleries in the suburbs of Paris. So why did we develop C-NEWTUN? First, several observations. When using or when modeling in 2D, the tunnel engineer must make several strong hypotheses, and also 2D cannot answer all the problems. There is sometimes, or sometimes, yes, the tunnel engineer has a lack of time to go to 3D, lack of time because he knows that it will cost time, or that he doesn't have enough background or experience on this 3D modeling, on this 3D models. So our vision with C-NEWTUN is to provide an intuitive 3D modeling environment, and also to propose optimized calculation times. Also, we observed that there are various methods used by tunnel engineers to model the tunnel construction. As illustration, I'm proposing here a figure illustrating the results of a benchmark proposed in France several years ago. And you see here the compilation of all the results, either 2D or 3D finite element method. And compared with the on-site measure, you see all the variations that that was proposed. So it illustrates that engineers have their own method, own background on tunnel modeling, and it requires to sum up somewhere these methods, and we propose to sum up them like the volume loss. So there is an imposed strain on the excavation. You can also model the shield process with pressure, and also you can model the shield process by imposing a contraction. So again, our vision with C-NEWTUN is to provide most of the standard methods, and also to provide an environment that can evolve with the new developments. So what you can do with C-NEWTUN? Nowadays, you can, in the actual version, generate conventional or TBM tunneling. The software is proposed to generate finite element 3D studies from A to Z, so from geometry to the results. But you can also use it as a tool for generating parametric studies, for example, on soil parameters, or in configuration of reinforcement, or more on several pressure influence. Also, as I will show later, we can use C-NEWTUN as a starter to access more advanced model. So let's start with the conventional tunneling. To see here through this movie what the user can do. So he accesses the grid with several steps for the definition of the soil, of the excavation, of the bolts, or the calculation process. You see that in few seconds, the 3D model is generated and meshed. All the stages of construction are edited. So this can be done for lateral bolts, radial bolts, or front bolts, and forepole umbrellas. And here you also access specific results, as I will show later, as well as you can access standard classic results, as we are in the 3D environment of CESAR. So let's see in detail these grids. We start with this welcome page, and here we access the general parameters page, where the user defines the type of sections covering most of the tunnel sections. User defines the soil layers. Here you can also define position the water table It can also specify if there are ground reinforcements, so radial bolts, front bolts, or Forepole umbrella. These can be combined or considered alone. And more, considering the Forepole umbrella, we introduced a stronger hypothesis on the geometry, as previous studies have shown that if there is a low inclination of this Forepole umbrella, then it has a minor influence on the total settlement. So let's see this live with the software. So we have here the welcome page, either for conventional excavation or TBM. I start here, it will create a new study. You see that we are in the CESAR 3D environment. Here I have the starting page. I can access all the various options, and especially here I will start, for example, with a face bolt and a Forepole umbrella. I will consider the symmetry hypothesis. I will consider the lining like surface bodies, and I will consider my my mesh density. So here I'm just generating the 3D geometry. I'm not doing all in. If I clicked on calculation, I will generate completely the model from the 3D geometry to the calculation and then access results. Here I just want to access the 3D geometry. I apply. And you see that in few seconds here, I am accessing the complete 3D model. And I see here the, oops, sorry, I went too far with my zoom. Okay, you see here the front bolts and the Forepole umbrella. Just to show you how quick it is to modify and generate another model, I'm now generating it with radial bolts. Again, I modify, I apply, and in few seconds, I get my new model with all the geometry modeling the excavation. Let's go back to the presentation and the details. So we have detailed the ground reinforcement types. Now, user will also access modeling options. So first, we will try to optimize the size of the model. So it requires that, of course, we will consider the symmetry. And also, we are respecting all the dimensions, like the lateral extension, and also the extension in front of the face excavation, so that we respect state of the art. Considering the lining, it can be modeled either in shell or volume elements. With shell, user will access directly the results. With volume elements, it will be more realistic, but it will also increase the number of nodes. Next, we will propose several mesh options to optimize again the size of the matrix. So we will propose an area of densification around the tunnel gallery. And also, we propose several mesh density presets from very low to high. And you see through these figures that there is a very high difference in number of elements. Of course, we do not recommend the very low setting, as it will be more used for debugging, for example. Let's just use medium high, or high setting. Finally, for this first page, user is is proposed several model operations. We call it all-in or step-by-step. By all-in, we consider that if you click calculation, you will get access to the 3D geometry and also to the results. So directly, all the process is generated and computed. When step-by-step will give the user the control to the geometry, to the mesh. Also, this step-by-step method will enable the user to access the geometry, so we can model other 3D or modify the 3D geometry. And finally, the step-by-step is also useful to edit the stages if user want edit the material properties, or if you want to add or remove the predefined loads. So when this first page is completed, user accesses the next one for the definition of soil properties. It starts with the definition of the initial stress field. It can be either a geostatic stress field or a self-weight procedure. So depending of this choice, of course, the parameters proposed are not the same. And if a water table is specified, of course, you will access effective stresses. When editing the soil properties, we have limited for this tool the constitutive model to a list of 4 First one is the standard Morcoulomb-plastic criterion associated to isotropic elasticity. So this is for soils. It is this constitutive model is very robust and with well-identified parameters. For more advanced a more advanced model is the hardening soil model, well known now for being efficient, for example, for shallow tunneling, but it requires also more parameters. The third law that we are proposing is ANL. This one is was developed by Nicolas Gilleron 10 years ago. ANL stands for A, anisotropy, NL, nonlinear elastic law, and it is associated with the Morcoulomb plasticity criterion. The influence of this model is very good on the shape of the settlement trough. You see here result gathered of measures with the symbols. There is a Gaussian curve like a peg curve for the fitting of this settlement trough, for the fitting of the measures. And you see the results with the ANL model, the curve named step 2 and step 3. These curves are also well fitting the measures. The last law that is proposed is the Hook-and-Brand, also well-known constitutive model for rocks with well-identified parameters. So next step after this is the definition of the excavation. The excavation can be either performed by full section or by upper and lower section. Also, user can define a delay for the raft and lining setup. So coming back to my model with radial bolts, I will now define the phases. I just apply, and you see in few seconds I'm generating all the excavations. If I have a look to the excavation, to the loads, you see here the tree on the right with all the stages, and you see here that, for example, the last excavation proposed here is well positioned. And now if I'm going back to my specialized tool, in my excavation parameters, I will define the delay. On the lining and on the raft, I'm adding one excavation step of delay. I'm also defining an upper and lower section. I apply, and again, it will erase the previous model, but in few seconds, generate the complete new model with new geometry, considering the upper and lower section, as we see here. And going to the loads, we have a new stages of construction. And if I'm going back, for example, to this one, we see here that the upper section is excavated, and we see also that there is a delay of 2 for the lining setup and a delay of 3 for the raft setup. So again, very easy to modify the tunneling conditions. Next, after definition of this excavation, we define the lining properties. Here, the lining can be either homogeneous, so for example, the user will be proposed a material library for the concrete, or it can be mixed. In this case, we consider concrete and arches, and from this material, we will calculate an homogenized modulus and an equivalent thickness, so that we reproduce correctly the effort, normal forces, and bending moment in the lining. So here again, user will access material library for concrete, and also a material library for the arches. The next step, we will define the raft properties. Now, again, access to the concrete library and a definition of a thickness. Next step, we will now define the soil reinforcement if they are activated. So let's consider that the face bolts are activated. I will define here the type of material. So from the library, I will define if it's in steel, if it's carbon or glass fiber, and I will also define a length and, more important, a density. This density, as you see here, will be reproduced as a grid of bolts. So the density will be transferred into a number of bolts. The same way, we'll define the radial bolts properties. Again, access to the material library, and definition of the distribution with an angular opening and a number of bolts per row. And finally, if we define, if we activate the Forepole umbrella, you access the angular opening and the number of tubes per row, and also a specific material library to define the tubes. Next stage is an important one. but with predefined values, so that user is not obliged to modify them. So we have here the calculation settings. Default ones are with the optimized algorithm, and also with an iteration process. Here, 200 iteration and a tolerance of 1%. That is considered as sufficient to access a good accuracy. Next step will also have an influence on the mesh. We defined the type of density. Now the measure must be also defined. We define if we select linear or quadratic interpolation. Default setting is on quadratic interpolation, as it is better for settlements calculation. And also we define a default factor of density to 0.98, as we have studied that this factor, it is not advised to reduce this factor. Of course, by reducing it, we will get less nodes, so quicker results. But we consider that it will also generate less less quality meshes, as we see here. Emphasize the distribution of nodes that is not very accurate, considering the 0.95 density factor. Last page that the user will access in the C-NEWTUN tool is an important one to optimize the calculation. We define here the steady state condition. This steady state condition is useful for the calculation of the total settlement trough. As we see here, the definition after Muller. And also this steady state condition defined by 3 criterions will be checked, and the calculation will be stopped if all the criterion are reached. First one, criterion 1, is about the stability of the incremental settlements from stage after stage. And the criterion 2 and 3 are here to define if the boundary conditions have no more influence on the results. So again, very important to have a stabilized calculation. And if these criterion are reached, and if the user goal with this analysis is to get, for example, the 3D settlement troughs, then it's enough. No need to calculate all the stages of excavation projected. We can stop at the current stage. As an illustration of what you can do with C-NEWTUN in a conventional tunneling, I'm proposing you this model where we have a Forepole umbrella, face bolts, and a concrete lining modeled in volumes. We reach the steady state condition after the sixth excavation. So it limited the total calculation time to 1 hour and 14 minutes. You see here the various calculation times produced. And as illustration, I'm going back to the tool. So I have prepared already this model, already calculated. So you see here all the grids that were used to define this model. And from this model, after calculation, we can access specific results. You see here a new grid with all the calculated excavation stages, and I can select them for the analysis. So the analysis will consider the incremental settlements. So it will generate it in a few seconds. You see here in the grid that the user can define what type of results he wants to be on his calculation report. So you find here the induced settlements, the total settlement trough, the 3D settlement trough, the volume loss, and also some cross sections. Here I have defined, for example, the cross section at the front, where I can see the horizontal displacement. So we have here the results with the transversal settlement trough, the 3D settlement trough that has been constructed from all the previous calculation, the calculation of the volume loss, and here at the front we see we have an illustration of the stability with the values of horizontal displacement. Again, this can be exported, saved, so that a user has directly his results. For more in-depth analysis of the model, as we are in the CESAR 3D environment, user can access the standard results. And here we can specify what stage we want to analyze. So let's go to the sixth one, the last one calculated. Here you see that we can display ISO values of any type of scalar. So here definition of all the you can specify the displacement, stresses, or other strains as results. If we select only the 1D bodies, we have here we can see here the front bolts and the forepole umbrella. So here we have the horizontal displacement, and if I selecting only the front bolts, for example, I can also go in details and see the efforts. So here, for example, the normal force. I will adjust the scale to this. Okay, and you can specify, we can get the maximum values here, and more in details, user can ask for specific values in the model, in each 1D element. So here refer to all the CESAR 3D result tools for more details. I'm going back to my presentation to introduce now, after the conventional tunneling, the other tunneling method proposed is TBM tunneling. So again, after the conventional excavation, we select the TBM tool. The grid will be updated. First page with general parameters will be quite similar, because we'll find again the definition of the layers, settings of the mesh, and other command tools. But we will also find specific settings. For example, the selection of the excavation modeling, either by deconfinement method from LGRI or imposed strain from Mohammed. I will detail it later. Of course, the tunnel geometry is simpler with only a circular shape. In conventional method, in deconfinement method, we'll define the excavation stages. So the shield length is function of the unit excavation, and also the total length of excavation is a function of this unit length. We need also to define the several pressures. So these pressures are first the front pressure, representing the action of the cutting wheel at the front, at the tunnel face. The shield pressure, simulating the mechanical interaction between the lateral face and the ground. And also the mortar pressure, with that will reflect the effect of the grout injection. If we select now the imposed strain method, so again, we will define the unit excavation length and the total length of excavations. And it requires also to define the imposed strain. So it will be either an isotropic one or an imposed strain in any direction. The imposed strain is imposed on the excavated ring, and all the previous excavated rings have a relatively high modulus with respect to the soil, so that we model only the imposed strain on the excavated ring. This method is already well documented. And final page that is different from the conventional tunneling. Here we find again the steady state conditions, but more interesting is that we introduced ground convergence control. So here user will define the authorized convergence at the key and at raft, and the software will calculate this convergence during all the calculation process, and we will stop the calculation automatically when this condition is no longer verified. So again, if this option is activated, it will stop the excavation process before all the excavation stages. So as illustration of this, I will present you an example with pressures. So you have here the presentation of the various soil layers and with the presence of water table. Steady state condition was reached after 16 excavation stages, and you see again a total time around 1 hour and 10 minutes. As illustration in details, so again here we have the model with the several grids that were used for the edition. Okay, with the various pressures. You see here as illustration the various loads that were applied. So again, as these pressures are automatically applied as illustration of the user edition, it is well controlled and well secured. So we have here the mortar pressure. We have here the shield pressure. We see here the front pressure varying with depth, and we have here the excavation pressure applied at the front and on the shield. And if we if we introduce some transparency, we will see that as we are below the water table, there is also an hydrostatic pressure applied as we have defined the self-weight of the new lining applied on this at this stage. If we go to specific results, again, you can access the same type of parameters with the settlement trough, the transversal settlement trough, and the complete 3D settlement trough, and other cut at the face and or longitudinal. Again, as we are in the CESAR 3D environment, you can access more detailed results in terms of isoscalar values. If we go, if we want to see the effort in the lining modeled here in volume, we can display the tensors. And again, I will adjust them here. Size, okay. So you access here the tensor, and you can ask for more detailed values. And more, if you want, to go in more detailed results, you can ask for you can define some some charts here with for example, we display the vertical settlements along this settlement trough. So again, a tool for complete analysis of TBM modeling in 3D. If I'm coming back now to my presentation, I can now introduce what you can do with C-NEWTUN to access more advanced models. First, you can add a pile foundation. This pile foundation is defined here. So you activate the pile foundation, and it will bring a new page for the pile group definition. First, we define if we want one or several pile groups. So it can be one only pile or several pile groups. The piles will be modeled either in 1D beam element or in 3D volume elements. Again, with 3D more realistic geometry, but more complex meshes, so more nodes and more calculation times. But also we are proposing a mix with 3D volume elements and a 1D dummy beam element, so that we get directly the efforts along the pile. Next, we are also defining the geometry of the pile group with the section of the pile, the spacing between each pile, and the distance and an orientation relatively to the tunnel axis, so that you can position correctly the pile group relatively to the tunnel, as we want to have the good influence of the tunneling on the pile group. And more for this good modeling of the piles, you can apply a load either per pile or through support, and also define accurately the soil pile interaction by introducing some interaction laws on 1D body, so on the shaft and on the tip, or introduce interface interfaces on volume bodies so that you can set if the behavior is either friction, bonding, or slipping. For illustration of this, I'm proposing you a model based on the works of Mohammad. So you see here the pile integrated in the 3D model. You see the 3D mesh and some of the results. You see here on the left, the curve is presenting the settlement trough compared. So the C-NEWTUN result is a dashed line, and we compare it very good to the on-site result represent on-site measures represented by the cross. On the right, you see the variation of normal force inside the pile, and again you see that the dashed line with the C-NEWTUN result is well fitting the experimental values. Let's have a look to this model in detail. So again, here you see the grid with all the parameters, the tunnel geometry, and so on. And for the definition of pile, here only one, but it was used here. And you see here the soil pile interaction defined. And you see here the column friction applied to this pile. Again, you can access specific results. They are already presented here. So settlement trough and so on. And important also is to access specific results. For example, let's see how the pile is deforming with time. So you see after several excavation stages, we can see the deformation of the pile with a large scale. I will reduce it. Okay. So again, more advanced results for the tunnel engineer to access and integrate these results in his calculation report. Coming back to the presentation, I would like also to emphasize this model as if you remember earlier, I presented some results, some benchmark results. Of course, it's not we did not answer directly to this benchmark. We produced the results illustrated here by the star after the results of the benchmark with the C-NEWTUN tool, but you see that with the correct addition of parameters and with automatic generation of the meshes, application of the loads, and other optimized calculation, we reached this good result. So this was the first step for accessing more advanced 3D models. Next, user can access with C-NEWTUN as a starter. He can access the geometry, a more advanced geometry with the CESAR 3D tool. Illustrated here, we generated the intersection of the main gallery with an auxiliary gallery. So again, another type of calculation, but outside the C-NEWTUN tools, but inside the CESAR 3D environment. And again, in the CESAR 3D environment, a user can generate very detailed model. Another useful tool or other advanced 3D models is to access constitutive models if the predefined ones presented earlier are not sufficient. User can access other constitutive models, other pile interaction laws as well. And again, if the predefined loads are not enough to represent the reality of the model, user can access the definition of other loads or other boundary condition, as illustrated here. You see on the surface an additional load applied. Finally, the last type of advanced model that user can access, again, using C-NEWTUN as a tool to generate very quickly 3D models with variation in the configuration. Here, we are studying the face stability depending of the presence of front bolts. Without front bolts, we reached a safety factor of 1.5 after C5 reduction method. And with bolts, we reach a safety factor of 2.3. Again, this method can be used easily, as you have seen earlier that the bolt density is defined through a grid. It is easy to adjust the bolt density and to generate a new 3D model and calculate the new safety factor with this new model. So that completes overall presentation of what you can do with C-NEWTUN. Now let's sum up the benefits. As you have seen with these predefined grids, we provide security in the generation of the 3D models with well-tailored geometry and meshes. With automatic generation of the stages and automatic application of loads and boundary condition, user is also in a well-controlled environment. We are proposing tools so that we are optimizing the mesh, so number of nodes, size of the matrix, and reduction of the calculation times, and also with this permanent regime or steady state condition, we do not calculate excavation stages if they are not pertinent for accessing the settlements, for example. More, we provide professional results through predefined tools like the settlement trough and the face stability. And again, we've shown that inside the 3D environment of CESAR, you can access a complete set of results required for your tunnel analysis report. So this concludes my presentation, the introduction of the new C-NEWTUN. Feel free to contact us on our social networks. Thank you again for your attention, and let's keep in touch very soon. Thank you and goodbye.